So today's objective is to find the resistivity of 2 to 3 wires by plotting graph between potential difference and current. For the experiment, you will require 2 wires of unknown resistance. You will require 1 ammeter. You require 1 voltmeter of suitable range. You also require 1 rheostat, 1 dry cell battery or the battery eliminator, and finally you require one-way key as well. So one-way key you can avoid because if you're using battery eliminator, so key is already there with the battery eliminator. So one suggestion, as you carry out the experiment, the range of ammeter and the voltmeter, that should be same, and the choice of both the voltmeter and ammeter should be proper. This experiment is based on the Ohm's law, according to which current flowing through the conductor is directly proportional to potential drop across it. Thus, I, the current, is directly proportional to V, the potential difference. Conversely, we should be able to write V is proportional to I, so V is equals to Ri. The constant of proportionality R is called as the resistance of that conductor. Now you see, if we plot a graph V versus I, we get a straight line passing through the origin, and the slope of the graph should give us resistance. Further, we know that the resistance of the wire, which has the uniform area of cross section, is given by the expression R is equals to rho L by A. Here rho is stands for the resistivity of the wire, and the resistivity of the wire is equals to Ra by L. Now you see, the resistance of the wire can be obtained from the slope of the graph. The area can be found by noting down the radius of the wire using the screw gauge, and the length can be measured with the help of meter scale. So by knowing R, A and L, we should be able to find the resistivity of the wire. Now you see, you should understand this experiment requires to find resistivity using 2 to 3 wires. So what we should be doing, we will take up 2 resistance wires, and we'll plot the V versus I graph for both the wires, and these looks like this. Say this is for wire number 1 and this is for wire number 2. So these are the 2 graphs. We'll find out the slope of wire 1, that will give us resistance R1, and we should be able to find out the resistivity of this wire. Again, we'll find out the resistance of wire 2 by calculating its slope. So once the resistance is known, we'll put the area of cross section and the length to find the resistivity of the second wire. Now by default, we happen to choose both the wires of same material. So the resistivity rho 1 and rho 2, that will be nearly the same. We'll take out the average to find out the resistivity of the given wire. Now to the circuit diagram to carry out the experiment. Here is the required circuit diagram. All the symbols, they have the usual meaning. Just close the key. Once the key has been closed, current flows through the ammeter. Then to the resistance, the potential drop across the resistance could be measured using the voltmeter, and the current flowing through the circuit is measured with the help of this ammeter. Now the current flows through the rheostat, through this part of the resistance, and to the key and the negative terminal. This is how the current is flowing. And I see, while assembling the circuit diagram, what you should remember, current always enters through the positive terminal of the ammeter, then leaves the negative terminal. This is true irrespective of the type of circuit you are using. Current will always enter through the positive terminal of ammeter and will leave the negative terminal. When it comes connecting the voltmeter is always connected in parallel to a resistor, and should always remember that the positive terminal of the voltmeter is at the higher potential and the negative terminal is always at the lower potential. How do I know that this is this point? This point A is at higher potential, point B is at lower potential. It's obvious because current always flows from the higher potential to the lower potential. Now over here, this wire is connected to the rheostat, and then current flows through the part of the resistance of the rheostat to the negative terminal of the battery. If you look at the diagram, symbolic diagram over here, just try to replicate over here the positive current from positive terminal of the battery eliminator to the ammeter. Positive terminal of the battery to the positive terminal of ammeter. This is red as positive, and from negative to the positive terminal of the voltmeter, from negative to the positive terminal of the voltmeter, and you see negative terminal, from the negative terminal of the voltmeter to the positive terminal of the rheostat, the red terminal, and then the negative terminal of the rheostat to the battery. Now see, before you assemble the circuit, my suggestion is always connect this resistance wire across the voltmeter. The resistance wire across the voltmeter should always be connected before you attempt connecting the circuit diagram. Let's try to see how the circuit is assembled. This is the resistance wire, and we need to connect it first across the voltmeter. Let's do it. Now it's connected. If you want to see it over here, this is the voltmeter, and we have connected a resistance wire across the voltmeter. Now the remaining part of the circuit. Here is the battery eliminator. From positive terminal of the battery eliminator, this red happens to be the positive, we need to connect the positive terminal of the ammeter, and over here the positive terminal to the positive terminal of ammeter, and then next we need to connect negative terminal of the ammeter to the positive terminal of the voltmeter, and over here from the negative terminal of the ammeter to the positive terminal of the voltmeter, and then from the negative terminal of the voltmeter to the positive terminal of the rheostat, and over here from the negative terminal to the positive terminal of the rheostat, and finally from the negative terminal of the rheostat to the negative terminal of the battery eliminator. The circuit diagram is complete. I would like to mention the point that the battery eliminator has these two negative terminals. We can connect this point at either. This is your wish. Furthermore, in the case of battery eliminator, you can always interchange positive and negative terminal. It will not affect the way you carry out the experiment. To begin with the experiment, we must find the least count of various instruments used. Over here, if you see carefully, this is an milliammeter. Its first 10 divisions, they read 100 milliammeter. You noticed that 10 divisions, they read 100 milliampere. So one division will read 10 milliampere. This implies that the least count of a meter is 10 milliampere per division. Now look at the voltmeter. In fact, it is a millivoltmeter. Its first 10 divisions, they read 100 millivolt. Thus, 10 divisions of millivoltmeter read 100 millivolt. So one division will read 10 millivolt. So the least count of voltmeter is 10 millivolt per division. To begin the observations, we must switch on the battery allimeter. Once it has been switched on, we should slide the slider of the rheostat from right extreme to the left extreme, and we should try noticing the reading of ammeter and the voltmeter, and we see that the needle of the ammeter, this shifts to the extreme right all of a sudden. So avoid taking reading beyond that point and see the initial reading. So at this point of time, the rheostat is on my right extreme, and the initial reading seems to be somewhere around 3 divisions. So we need to begin it from 4 division of milliammeter, and the maximum reading that could be somewhere, as you noticed, could be somewhere 200 milliampere. So these could be the possible limitations before we start taking the readings. At this point of time, slider is on my extreme right. I am sliding this towards the left side while looking at the ammeter. I'll keep sliding till the needle is close to 4th division. So this is 3, this is 4th division. At this point of time, needle is coinciding with the 4th division, and the corresponding reading in the voltmeter is 12 divisions. And let's record the first reading over here. Number of divisions, this is ammeter reading. Number of divisions, there are 4 multiplied by least count, this happens to be 10, and the total reading, this got to be how much? This got to be 40 milliampere. And over here, the number of divisions, there were 12 divisions, and the least count was 10 millivolt per division, and this is equals to how much? 120 millivolt. And if you divided V by I, this is equals to how much? 3 ohm. 120 divided by 40, and this is equals to 3 ohm. Now next, I will slide the slider towards my left and will record the reading over here. Now as I slide it further, let's see that what happens. Current is increasing, and from 2 to 6 divisions, 2 to 6 divisions at this point of time, number of divisions in the millimeter now has gone to 6. And let's see the reading of the voltmeter. The reading of voltmeter happens to be 18 millivolt. Let's record it. So this is equals to 6th division multiplied by 10 milliampere per division, and this is equals to how much? This is 60 milliampere. And over here, this is 18 division multiplied by 10 millivolt per division. This is equals to how much? This is equals to 180 millivolt. Divided. Now as I divide, again I get 3 ohm. For the third reading, I need to repeat the process. It means I need to slide this slider further on the left. Now as it slide it further on the left, I'll try to ensure that the reading in the ammeter has increased to 8 divisions. So this is reading of ammeter, and the corresponding reading of voltmeter happens to be 24 divisions. So this is 8 division multiplied by 10 milliampere per division, and this is equals to how much? 80 milliamperes. And over here this is 16, this is how much? This is 24 division multiplied by 10 millivolt per division, and this is equals to how much? This is 240 millivolt. So further, as you divide, this is equals to how much? 3 ohm. Similarly, you can record fourth and the fifth reading as well. So here is a table of 5 observations. The average value of the resistance that turns out to be 3.0 ohm. Now we need to repeat this experiment for another wire of same material and preferably half the length of previous or double the length of previous, whatever may be the case. In the previous case, the length of the wire I chose was 50 centimeter. Now the length of wire used, this is 25 centimeter. So I already know the resistance of this wire got to be half of the previous value. As we carry out this experiment with a wire of same material but of shorter length, preferably half the previous length as I have already suggested, then these are the readings I observed. My suggestion is keep this column same. This column same, I mean take reading for 4th division, then for the 6th division, then for the 8th division in multiple of 2. This is what you understand. So my observation was when the reading of a meter was 40 milliampere, then the reading was voltmeter was 60 milliampere, and the resistance is 1.5 ohm for this set of I and D. For the second set, when the reading of meter was 60 milliampere, the reading of voltmeter was 90 milliampere. So again the resistance turned out to be 1.5 ohm. So for all the readings, for all 5 set of readings, the resistance turned out to be 1.5 ohm as expected. The length of wire was shortened to half, so obviously the resistance will drop to half only. Yes, the average value in this case, this got to be how much? This got to be 1.5 ohm. I was little fortunate as I carried out this experiment. This is just a coincidence that all the value they fall nearly perfect. In your case, when you're carrying out the experiment, you can notice there could be a slight difference. It could be 8 division or could be 10 division. This could be 13 or 11. But you should record whatever the reading they are. If it is 14, then write 140 millivolt, and accordingly you should choose the value. You should calculate the value of resistance. Take out the average. That will be the average resistance of the shorter wire. Now, so here is an important point. Though we have calculated average value of resistance from the table, but when it comes to the calculation of the resistivity for the experiment, you must find the value of R using the graph. So let's plot the graph as suggested by the observations. Before you start plotting the graph, you must choose the scale. As I look at my observations of first table, the maximum value of current, that was 120 milliampere. So 120 milliampere, and in the graph sheet, if I choose one big division on axis of x to be 1 milliampere, means I'll have to choose 12 boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This may get little bigger. So the correct choice to me, it appears to be, let's choose one division on along axis of x to be 20 milliampere and one division along axis of y to be 40 millivolt. So this is the 20 milliampere mark, this is 40 milliampere mark, this is 60 milliampere, this is 80 milliampere, this is 100 milliampere, this is 120 milliampere, and on axis of y, one division that was 40 millivolt, let's choose to be, this is 40 millivolt, this is 80 millivolt, this is 120 millivolt, this is 160 millivolt, this is 200 millivolt, this is 240 millivolt. So this is okay, this seems to be okay. The first reading it was for 40 milliampere it was 120. So for 40 milliampere it was 120. So this is the point. For 40 milliampere the reading of voltmeter was 120, and for the 60 it was 180. 60 it was 180. So this is 160, this is 200, so this is 180. This is perfectly okay. Then for 80 it is 240. 80 it is 240. 80 it is 240. And for 100 it was 300, it was 100, it was 300, so I need to draw it further. So this is 240, then 280, then 320. This turns out to be somewhere here. So this is all okay. So it seems now I need to join these points, and as I join these points I already know that V is proportional to I, so the graph that must pass through the origin. So I need to connect these points through a straight line, ensuring that as I draw this straight line must pass through the origin. Let's try doing it. So the idea is this may not be as perfect as I would have tried using a scale, and for the reading I have taken all the points, they must lie on the graph. But whenever you plot a graph and number of readings or more, then the graph it should be so that number one, most of the point they should lie on the straight line. Point number two, half of the remaining point they are on the top of the graph, and the remaining half of the left they are on the bottom of this graph. This should be the criteria. And if I plot it for the second wire, the graph it is for 40 milliampere. For 40 milliampere it was 60, and for 60 it was 90. For 100 it was 150. Again join these points to obtain the next graph. This is the graph for the second wire. At 40 milliampere it was 60 millivolt, and for 60 milliampere it was 90 millivolt, and for 80 milliampere it was 120 millivolt, and for 100 it was around 150. For 120 it was 180. Join all those points to obtain the graph. To find the resistance of wire 1, let's choose this point and drop a perpendicular. We know this value is equals to how much? This is 180, and 180 divided by this value of current, which is 60, should give us the resistance. So the resistance of wire 1, delta V by delta I, and the value of delta V is equals to how much? This is 180. This is 180 millivolt upon, this is 60 milliampere, and this is equals to how much? This is equals to 3 ohms. To find the resistance of wire 2, let's choose this point and drop a perpendicular. So this value should give us the potential difference, that is equals to 120 millivolt, and this value should give us the current, corresponding value of current, which is equals to 80 milliampere. So the value of resistance of second wire, this is delta V by delta I, and this is equals to how much? 120 millivolt upon 80 milliampere, which happens to be equals to how much? This happens to be 1.5 ohm. The resistance of wire number 1 is 3 ohm. To find the resistivity, let's follow more calculations. For this wire, the radius of this wire is 0.17 millimeter, that makes 1.7 is to 10 power minus 4 meters. The area of cross section of the wire A is equals to pi r square. On solving, we get 9.07 is to 10 power minus 8 meters square. Because the length of the wire used is 50 centimeter, means half a meter. Substitute value of R1, A and L. the value of the resistivity of the wire that comes to be 54.4 is to 10 to the minus 8 ohm meter. Now to find the resistivity of second wire, we'll use the value R2. R2 is equals to 1.5 ohm, and you see row 2, as we substitute value of R to be 1.5 ohm, the value of area of cross section got to be the same. There is only change in the length. This is 9.07 is to 10 is to the power minus 8. Length is 25 centimeter, that makes 1/4 of a meter. Solve it. The value of rho 2, this is again equals to 54.4 is to 10 is to the power minus 8 ohm meter. Take the average of the two, that should give us the resistivity, and the average value got to be only 54.4 is to 10 is to the power minus 8 ohm meter. In the calculated value of resistivities, take the average as is done so. Thank you.